Right, then let's look at the work problems for this chapter. Again, the problems could be taken from either Brown and LeMay's chemistry or from Zumdahl's chemistry, or some of the multiple choices especially are taken from Mr. Mack's AP Chemistry website. There may be occasionally a problem from McMurray and Fay Chemistry. Answers are provided by the author. Next slide. Next. All right, so here we have a situation. Which of the following solutions of strong electrolytes contains the largest number of moles of chloride ions? So we had a problem like this when we did the lecture notes for this chapter, and so we want to multiply these two things together, the moles per liter times liters, to get the number of moles of the formula unit, and then we have to multiply times how many particles these things are going to break up into. So just look at A. I'm going to change that from 100 milliliters to 0.1 liters and multiply that times 0.3 moles per liter over here, and that's going to give me 0.03 moles of AlCl3. But then, as we said in the lecture notes, we then have to in turn multiply that by 4 because the AlCl3 will break up into 4 particles. So let's just look at the number that they're going to break up into. AlCl3 will break up into 4. MgCl2 will break up into 3, and NaCl will break up into 2. So those will be the last things we multiply. What about sucrose or something like that? Well, those won't break up at all. So the number of particles would just be 1. The reason is because things like sucrose and glucose are covalent compounds. So they don't break up when you put them into water. So for B, you would have 0.05 liters here times 0.6, and for C you would have 0.2 liters times 0.4, which is 0.08, and then multiply it by by 2. And let's go to the answer. So when we do A, when we do all this multiplication here, we get 0.09. For B, we get 0.06, and for C, we get 0.08. So the largest of those three numbers is A, 0.09. Next slide. How would you prepare 2 liters of the following solution? 0.25 molar. Means that we need to have, for 1 liter, that's 0.25 moles per liter. So if we wanted 1 liter, we would have to have 0.25 moles of NaOH. NaOH turns out to weigh 40 grams per mole. So 0.25, 1/4 of that would be 10 grams. But we want to make 2 liters here, not 1. So instead of having only 10 grams of NaOH, we'd have to have twice that much because we're trying to make twice as much as 1 liter. We're trying to make 2 liters. All right, so look up Na, O, and H if you don't remember them. In your chart, Na is 23, O is 16, and H is 1. So 23 plus 16 plus 1 is 40 grams per mole for NaOH. So if I wanted to make 1 molar, I'd have to have 40 grams of it, but I don't. I want to make 1/4 or 0.25 molar. So 0.25 times 40 is 10. So if I wanted to make 1 liter of if I wanted to make 1 liter 0.25 molar NaOH, I'd have to have 10 grams of NaOH. So I would have to take NaOH powder and weigh out or mass out 10 grams. But I have to have twice that much here, so I'd have to mass out 20 grams. So to make it, I'd just mass out 20 grams of NaOH powder and put it into 2 liters of water. And that's all there is to this. Next slide. Next. All right, this one is just like, it's not hard, it's just you have to do it in several steps. So let's do this together. So ammonium is NH4, so that would be, and then sulfate is SO4. Sulfate's 2 minus, so you'd have to have 2 of the ammoniums. So it'd be NH4, 2 SO4, which that's actually a little bit too much for me to try to figure out the molar mass of that. So anyway, whatever the molar mass is from ammonium sulfate, which is going to be shown on the answer slide, you would divide how much you have, which is 10.8 grams, right, by whatever 1 mole weighs. So just add this. It's going to be NH42, so it'd be 2 times 14 for the N and so forth. So add all of that together, divide that by 10.8, and that will give you the number of moles that you have to start with of the ammonium sulfate. So what you would want to do then, it says it's in enough water to make 100 milliliters of solution, so that's 1/10 of a liter. So whatever you get for your number of moles here anyway, when you divide the 10.8 by the molar mass of ammonium sulfate, that's going to give you some number. And then you would divide that by 0.1 liters to get the molarity. So I said this is going to take a few steps. And then what you would want to do is you want to see how many moles you would have if you took 10 milliliters of that. So all you have to do is realize that I have, let's say, well, let me just take a guess, 10, 11, let's just say it's 0.1 molar. And if you divide that, 10 grams, let's see, okay, hold on, 10, 11 divided by, let's just say 100 would be about 0.1 divided by 0.1. So let's just say that we wind up with one. Actually, this is too much for me to do in my head. Anyway, let me go ahead and run through the basics of it here, and then I'll go ahead and go to the answers, and we'll go through it again. All right, so whatever we get here, we figure out how many moles we have, and then we put it in 0.1 liters. So the molarity of that would be however many moles we have divided by 0.1 liters. And then you would multiply that molarity of your solution here times 0.01 liters, because that's what 10 milliliters is. It's 0.01 liters. So you would multiply the molarity of your solution times 0.01 liters, and that's going to tell you how many moles you have of the ammonium sulfate in your little sample that has only 10 milliliters in it. And then once you know that, you know the number of moles of the ammonium sulfate, then the last steps is you add it to 50 milliliters of water. So your total volume would be 60 milliliters of your final thing that you end up with here. It's 10 plus 50 is 60, but I would convert that to 0.06 liters. So you would then just take the number of moles that you came up with in the previous step and divide it by 0.06 liters. Let's go ahead and go to the next slide. So when we do this, it turns out that actually the NH42SO4, when you add up all of these masses here, for the N's, the H's, and the S's, and the O's, you get 132, okay? You'll want to make sure that you can do that, so you might want to try it on your own and make sure you get the right answer. So anyway, you divide how much you have, which is 10.8 grams, divided by how much 1 mole weighs, which is 132 grams, and you get 0.0818 moles, and that's how much you have to start with. And then you're going to put that in 100 milliliters of solution, or 0.1 liter. So divide by 0.1 liter. So just bring this over here and divide it by 0.1, and you're going to get that you have a concentration in moles per liter of 0.818. Then you're only going to take 10 milliliters of that, or 0.01 liters of that. So your molarity is 0.818, which you figured out on the last step. And you're only taking 10 milliliters or 0.01 liters of that. So multiply 0.818 moles per liter times 0.01 liters, and you're going to get an answer in moles where the liters are going to cancel, and you're going to get 0.00818 moles in that 10 liter sample, which you're going to then dilute to 60 milliliters by adding 50 milliliters of water. So you'll then have that same 0.00818 moles, but now it's going to be in 60 milliliters, or 0.06 liters. So just divide 0.00818 by 0.06 liters, and here's your final concentration. Now let's go back. Okay, so what they want us to do now, the 0.136 molar that you see right there is the concentration of that whole thing. But because this is an ionic compound, what's going to happen when you put it in water? Well, it's going to break up into 2 NH4 pluses and 1 SO42 minus. So the concentration of the SO4 is going to be the same as the whole unit, because there's a 1-to-1 relationship between the SO4s and the NH42 SO4s. In other words, every time you break up an NH42 SO4, you're going to produce 1 SO4. But you're going to produce 2 NH4s, so the concentration of those is going to be twice the concentration of the formula unit. In other words, 2 times 0.136, which is going to be 0.273. So the concentration for the NH4 will be 0.273. The concentration for the SO4 will be 0.136. Next slide. All right, let's predict which of these are likely to be soluble. So let's just do these one at a time. Aluminum nitrate. The rule here is that nitrates are always soluble. So this one will be soluble, so let's put a check. Magnesium chloride. Chlorides are always soluble unless silver, mercury, or lead are with them. And magnesium is not silver, mercury, or lead, so this will be soluble. Sulfates are always soluble unless it's mercury, lead, barium, or calcium. mercury, lead, barium, or calcium, and rubidium is not one of the four things I just mentioned, so this one is soluble. Now from here down, from C down, the things are going to be insoluble basically, unless it's one of the exceptions. So hydroxides will be soluble if it's sodium, potassium, lithium, rubidium, cesium, calcium, or barium. And nickel is none of those, so this will not be soluble. Now be careful here, because when we're going from C to D, we're switching from things that are usually soluble to things that are usually not soluble. Sulfides here are only soluble if they're mixed up with things in the first column, like, for example, lithium and potassium and sodium, and lead isn't in that column. So that means sulfides here, this sulfide will not be soluble. Hydroxides, we just did that. Magnesium is not one of those 7 that we mentioned, so it is not soluble. And phosphates also are in that last category, where the only time they are soluble is if they're in conjunction with something in the first column, which this isn't. Okay, so the first 3 will be soluble. The next 4 will not. Next slide. So here's your rules again. Next slide. And here are your answers. If you want to pause here and look at these, you can. Otherwise, let's go to the next slide. If we mix these 2 solutions together for A, B, C, and D here, will there be a precipitate? So let's do this. Start with a Fe would be mixing with chloride here. Chlorides are always soluble unless they're with silver, mercury, or lead, which Fe is not that, so that will be soluble. Sulfates here are always soluble unless they're with barium, calcium, mercury, or lead, and potassium's none of those, so this is going to be soluble here. So we want to know for each of these what precipitate will form, if any. So these are not going to make any, so this is going to be none. I'm just going to put an X here. All right, B, aluminum mixed with hydroxide. That's not one of the hydroxides that's soluble, so it's going to make a precipitate of aluminum hydroxide. And this is the +3 state of aluminum because it's associated with 3 nitrates. So we're going to have 3 of the OH minuses. So this is going to make a precipitate here, aluminum hydroxide. And the barium nitrate will be soluble. So there's our precipitate. For C, calcium is one of the 4 things that when it bumps into a sulfate, it is a precipitate. So Ca is +2 and SO4 is -2. So these match up perfectly. So our precipitate will be CaSO4. And then for part D, potassium won't make a precipitate, nitrate won't make a precipitate. What about nickel sulfide? Yes, because sulfides are only soluble in conjunction with things from the first column, and nickel isn't in the first column. Now these things are a lot easier to do once you get used to what elements are in what columns, and you don't have to know them all, but especially if I were you, I would try to focus on which elements are in the first and second and 7th columns for right now, because that'll help you out. Okay, so here are the answers. So let's go to the answer slide, and then I'm gonna, if you want to pause on that one, let's move. Oops, there's the rules again. And next slide, here are the answers for A and B, and here is C and D. You can pause these if you want to, otherwise I'm going to go on to the next slide. So write net ionic equations for this. So we've got ammonium sulfate and barium nitrate. So we're going to have NH4, which I should maybe not have tried to write this out. NH4, so I'm not going to put the other parentheses, and then SO4. So that's ammonium sulfate, which is soluble. Sulfates are soluble unless it's mercury, lead, barium, or calcium. And then we're adding that to barium nitrate, which is going to be BaNO3, which I rapidly lose patience when I try to write these things. I know it's helpful to you, but it's using up such an enormous amount of time because this thing is so inefficient. So NO3, and then we have to have 2 of those because the NO3s are -1 and the bariums are +2. So there we go. Anyway, so what's going to happen? Well, the NH4 is going to match up with the NO3. That's soluble, but when the barium comes in contact with the sulfate, that's not soluble, so it's going to precipitate out as barium sulfate. And I'm not going to write that out. So BaSO4 is going to precipitate out. So the way that we would do this would be to go ahead and write the net ionic reaction. Now, if you want to, you can write out the complete ionic and all of that stuff, but you don't have to because they're not asking you to do that. So if we know that we're going to wind up with a precipitate of barium sulfate, BaSO4, then what we can do is we can just write Ba2 plus SO42 minus gives BaSO4, and that's the answer to the question here. So next slide. So we wind up with just that. So here's your answer. Now, if you want to write out the complete ionic equation, this is what it would look like, and everything I have a circle around here is something that is not involved in the actual reaction. So these are all called spectator ions, all of these things in the blue circles. So the formula equation would be here, and what I did was I took what I started with and then I mixed and matched this thing on the left with this on the right, and this on the left with this on the right here, and put them over here on the product side over here, and then I balanced it, which in order to do that, it turns out all I had to do is put a 2 there. All right, so you can look at this as long as you want to. Next slide. 25 milliliters, which let's immediately convert that to liters, so that would be 0.025 liters of HCl. And the reason I do that is it's just easier to do it if you just change it to liters, and then you can multiply times moles per liter. And I'm not sure why, but some other teachers just love doing it with things like milliliters and millimoles, and I just never understood that. Okay, so 0.025 liters HCl, and that's all we know about the HCl, so this is it. And then for the NaOH over here, we know that it's 0.0246, 0.02416, so it's 0.024. Forever to write this stuff. It's just, I'm not really a huge fan of like Excel and PowerPoint and Word because they just seem to make things sometimes, I mean, I really do appreciate them at the end of the day, but anyway, so 0.02416 liters of NaOH, where I just rewrote milliliters as liters, and it's 0.106 molar, so I'm going to multiply 0.106 moles per liter times 0.02416 liters, and that's going to give me my number of moles of NaOH, and that's going to equal the number of moles of the HCl. So whatever number I get when I multiply 0.02416 times 0.106 is going to have to equal what I get when I multiply 0.025 liters of HCl times its molarity. So we can call the molarity like M, or we can call it X or whatever. We just want to solve for that. So let's go to the next slide. So when we multiplied these two things for the NaOH here, we got 0.00256. What that's telling us is that we have to also have the same number of moles of the HCl. In other words, we have to have 0.00256 moles of HCl as well, because it has to balance. It has to be the same for titration. In order for both of them to be completely wiped out, you have to have the same number of moles of both. So what that means is that for the HCl, we have to multiply 0.02416 liters times X, and that's going to give us 0.00256. So you can just divide 0.00256 by 0.02416, and that will give you your answer. And that's kind of what's actually done here. So down at the bottom, these three steps here, divide the 0.00256 by the 0.025 liters, and I'm not sure where the 0.025 came from, but anyway, and you get that the this right here is wrong. It should be 0.02416. I must have rounded it off, but I didn't round it off right either. It should be 0.024, but anyway. So I don't know, this answer that I have here is 0.102. I don't know, that may be off a little bit if I used 0.025. I'm not sure what happened here, and I didn't catch it before I abridged these slides, so, but it's close enough. Anyway, what I got was 0.102, so you may get a slightly different answer. I'm not sure about that. I'm not sure if this 0.102 was using 0.02416 or if it was using 0.025. So apologies about that. But anyway, the answer is going to be about 0.1 molar. Next slide. All right, so we have sodium metal, so that's just going to be Na, and it has an oxidation number of 0 because it's a pure metal. And then we have F2 gas, and the oxidation number is 0 on that also. So F2, so we're adding these, we're reacting them. So on the other side, we're going to wind up with NaF. So we have an arrow, and then we have NaF over here. And it would be NaF because Na is +1, right, and F's -1. So there we go. And so we're supposed to balance it. And you could just probably look at that and say, okay, we got to have a 2 here. Got to have a 2 here, so that means we have to have a 2 here, right? But we're also supposed to look at these charges. So let's just go to the next slide. So Na here is going from 0 to +1. That means it's losing an electron. And the F2 is going from 0, and it's becoming -1. And the reason is because here the Na is going to be +1, and here the F is going to be -1. And the reason is because the Na is actually giving up an electron to the fluorine. So Na is going from 0 to +1, so it's being oxidized, and F is going from 0 to -1. That's actually going to have to happen 2 times here. This one's going to have to happen twice because you start with 2 F's instead of 1. So, but anyway, it's gaining an electron, so it's being reduced. But it's gaining 2 electrons here, so we need to somehow take that into account in addition to the Na's and the F's to balance this. Well, again, as we did in the lecture notes, if you watched those, we found out that if we just looked at it and balanced it the way we think it should be balanced, which would be to put a 2 in front of the NaF, and then that means you have to put a 2 in front of the Na. It just so happens that that also balances it for charge, but it doesn't always happen that way. So anyway, in this particular case, what we're going to do is we're going to match up the number of electrons on the left and on the right because the charge also has to balance out. So for the F's, since there are 2 of them, that means that we're going to have to gain 2 electrons. So that means that we would have to have 2 of the sodiums here to balance that. So, and that's just to do with the electron numbers. And it turns out that that also balances the elements. But anyway, so we have to put a 2 there, and also that means that we have to have, when we balance for the elements, we also have to have a 2 over here in front of the NaF. And then that's balanced for both the Na's and the F's, and also for the charges. So now on the left we've got 0 and 0, 0, and on the right we have 1, -1 is 0. Next slide. All right, let's go to the multiple choices next. Concentration of species. So we've got 2.104 molar solution sodium sulfate. So we're going to have to figure out the formula for sodium sulfate. And we know that Na is +1 because it's in the first column, and sulfate is SO4 2-. So we're going to have 2 of the Na. So it's going to be Na2SO4. So that means that is going to be the formula unit, and that's what this concentration means. When it says 2.104 molar, it's talking about this when we first add it to the water. So the concentration of the whole thing here is 2.104, which I'm just going to write 2.1. Try to write 2.1. Okay, so whenever one of these things here breaks up, how many SO4s will be produced? And the answer is 1. Because there's a 1-to-1 relationship. Every one of these whole formula units has 1 SO4 in it, right? Because, I mean, there's only 1 of them, but there's 2 NAs. So every time one of these units breaks up here, it's going to produce 2 of the NAs. So in other words, what we're saying here is that if the initial concentration of the whole thing is 2.1 molar approximately, then the concentration of the SO4 will also be that, because it's 1-to-1, but the NAs are 2-to-1, so they'll be twice as much. So for the NAs, it's going to be 2 times 2.1, which would be 4.2. So it looks like A is going to be the correct answer here. We're going to have, let's see, is that the right order? Yeah, so for the sodiums, it's going to be 4.2, so that would be this, and then for the sulfates, it's going to be 2.1. So the answer here is going to be A, it looks like. Okay, let's go to the next slide. And here you can read this on your own if you want to. Next slide. What is the molarity of a solution prepared by diluting? So we're going to start with 43.72 milliliters here of 1.005 molar and dilute it to 500. So the 500 is going to be V2. which I'll just write it very quickly. What's going to be V1? It's going to be this. And this thing right here is going to be M1. So we want to use M1 V1 equals M2 V2, which I would ordinarily write that out, but it just takes too much time. So I'm just going to say it again. M1 V1 equals M2 V2, where we know M1 and V1. Here's V1, which we're going to convert to liters. It's 0.04372 liters. And here's M1, which is 1.005 moles per liter. And then here we have V2 is going to be 0.5 liters. And then the M2 is what we're looking for. So to solve for that, we would multiply M1 times V1 and then divide by V2, and that's going to give us our answer. So let me just look at this for a minute and see if I can do this. So it's about, yeah, I can't do that. Let's go to the answer. All right, so here is our formula. So M1 V1 equals M2 V2. So M2 is going to be M1 V1 divided by V2. And we know all of those things because they were given to us in the problem statement. Again, notice that I've converted the numbers of milliliters to liters here. So when you do your multiplying and dividing, you get 0.0879 for your answer, and that's the second molarity. That's the final molarity. So find 0.0879, and it turns out that's answer choice C. Next slide. When aqueous solutions of blank are mixed, a precipitate is formed, and we have 5 choices. And it looks like only one of these can be correct, and I can just look at it and see the answer. But let's go through all of them. I'm almost at my limit that I want to spend on this. But anyway, let's just quickly go through all of these. If I mix Na with Br, let's see, that's going to be soluble. Ki will be soluble. Lithium iodide will be soluble. Cesium carbonate will be soluble. Most of these are in the first column, so those are always soluble. So is K, and Cl is in the 7th column. Chlorides are always soluble except for silver, mercury, and lead. Chromium sulfate. Let's see, chromium and sulfate. So sulfates are always soluble except for mercury, lead, calcium, and barium, and chromium is not one of those 4, so those are all soluble. Let's skip D for right now. Come to E. Potassium's in the first column, always soluble. Nitrate's always soluble. Barium and hydroxide here. Barium hydroxide is one of the 7 hydroxides that we're going to consider to be soluble. And again, just to review, that's sodium hydroxide, potassium, lithium, cesium, rubidium, barium, and calcium. So that leaves D. Okay, so what's wrong with D? Well, if you have silver, remember that silver, mercury, and lead will make either chloride, bromide, or iodide insoluble. So whenever the Br minuses come off and hit the Ag pluses here, they're going to make a precipitate of AgBr. So answer choice D is going to be correct. All right, let's move on. We're almost out of time. Next slide. Next slide. And here is your answer. Next slide. And what are the spectator ions between KOH and HNO3? So H here is going to match up with the OH minus here to make water. So this is KOH is a strong base, HNO3 is a strong acid. So those two things are going to make water. And then the NO3 minus is a spectator ion, and the K plus is a spectator ion. So the answer choice here is going to be C. Next slide. And here are your answers, which I'll let you look at. I'm going to go ahead and cut this short because I think for this particular problem set, 30 minutes is enough. And we're at 29 minutes right now, so let's go ahead and stop this. So that's it for Chapter 4. If you have time, in addition to the ones we just did, you should maybe go to Mr. Mack's website or some other website, or just look in the back of the Chapter 4, look at the problems at the end of the chapter in Brown and LeMay or some other chemistry textbook on this same topic, and do some extra ones if you have time. But again, as I say every time, I try to remember to say, don't do a lot. Just do one at a time and make sure you understand it. Don't put yourself in the position of trying to do a whole bunch of them and then you don't know how to do any of them. You see what I'm saying? So just do them. I recommend that you just do them one at a time and then make sure you understand that one before you go to another one. So let's stop, and I'll see you in Chapter 5.